All right, this is example 6, and it came from the 1999 exam, BC4, where the calculator was allowed. So we're going to use a calculator on this too, okay? So the function f has derivatives in all orders for all real numbers x. Assume that f of 2 is -3, f prime of 2 is 5, f double prime of 2 is 3, and f triple prime of 2 is -8. Write the third degree Taylor polynomial for f about x equals 2. So that's the center, okay? And use it to approximate f of 1.5. Okay, so let's first write this third degree Taylor polynomial, okay? So this would be p sub 3 of x, okay? And so it would be the 0th derivative, right, which would be f of 2 over 0 factorial, that'd be 1, times x to the 0th, that'd be 1. So that's why we're not going to write it. And then plus f prime of 2, okay, over 1 factorial, but 1 factorial is 1, that's why we're not going to write it, and then times. Now, we're centering at x equals 2, so we do want to multiply this by x minus 2, okay, and then plus f double prime at 2 over 2 factorial times x minus 2 squared. And then, okay, so that would be a third degree Taylor polynomial, or a third order Taylor polynomial, or sorry, second degree, second order, okay? So we need a third degree or a third order, okay? That would be plus f triple prime at 2 over 3 factorial times x minus 2 cubed, okay? So now, because of this, we can just put these numbers in, okay? So p sub 3 of x would be, well, f of 2, that's just -3. And f prime of 2 is 5, so that'd be plus 5 times x minus 2. And then f double prime is 3, so this would be plus, so this would be 3 over 2 factorial. Well, 2 factorial is 2, so it'd be 3 over 2 times x minus 2 quantity, the x minus 2 quantity squared. And then f triple prime of 2 is -8 and over 3 factorial. Now, because this is negative, we're going to write minus, and it's going to be 8 over 3 factorial, which is 3 times 2 times 1. So that'd be 6 times x minus 2 cubed. Okay, so that means the third degree Taylor polynomial, cleaned up a little bit, because one of these we can clean up, would be -3 plus 5 times x minus 2 plus 3/2 times x minus 2 squared minus, and this can be reduced to 4/3 times x minus 2 cubed. All right, so now what we want to do is we want to use this Taylor polynomial to approximate f of 1.5. Okay, so we're going to write f of 1.5. Okay, this is going to be really, really important here, okay? This is not equal to, it's an approximation. So we must, it's not one of those, it doesn't matter if you do or if you don't. It really does. They'll take off points if you don't, okay? So this is going to be approximately, all right? And we're going to put 1.5 in everywhere we see the x. So this would be -3 plus 5 times, and that'd be 1.5 minus 2 plus 3/2 times 1.5 minus 2 squared, and then minus 4/3 times 1.5 minus 2 cubed. Well, 1.5 minus 2 for this one, and this one, well, that would just be -0.5. So this is about -3 plus 5 times -0.5 plus 3/2 times -0.5 squared minus 4/3 times -0.5 cubed. And we're going to put that into our calculator. So I'm going to go to the graphing calculator now, okay? Okay, so with our graphing calculator, we're going to put this in. It's -3, and then plus 5 times negative 0.5. And then plus 3/2 times negative 0.5 squared, and then minus 4/3 and times negative 0.5 cubed. Okay, and you wind up with negative 4.958. So the approximation would be negative 4.958. So from our graphing calculator, we got an approximation of negative 4.958. Okay, let's go to part B. All right, for part B, the fourth derivative of f satisfies the inequality. The fourth derivative of x, absolute value of that, is less than or equal to 3 for all x in the closed interval 1.5 to 2 closed interval. Use the Lagrange error bound on the approximation of f of 1.5, which that's what we found in part A, to explain why f of 1.5 cannot equal negative 5. Okay, so we found an approximation for f of 1.5. We need to find the error at 1.5. Okay, so this would be the absolute value of r sub 3 at 1.5. Okay, so that's the x value that we're finding the remainder for, okay, or the error for. Okay, so we know that this is equal to the absolute value of the fourth derivative, because it's n plus 1. So the fourth derivative at some value c that we don't know the c value over 4 factorial, and then times, and it would be 1.5, because that's my x, 1.5 minus 2 raised to the fourth power, and close the absolute value. Okay, so now we know that this right here, okay, we know from up here that the maximum of this, right, has to be less than or equal to 3. Okay, so this is the same for some c, right, between 1.5 and 2. Okay, but we know the maximum of this, so this needs to be less than or equal to the absolute value of this, right, which would be less than 3. So absolute value of 3, okay, over 4 factorial times 1.5 minus 2, but that's going to be negative, but this is inside an absolute value. So this is really times the absolute value of 1.5 minus 2 raised to the fourth power. Okay, this would be 3, this would be 4 factorial. Okay, so I know that the error at 1.5 would be less than or equal to, okay, and I'm going to put this into my calculator. Okay, all right, I'm going to go do that right now. All right, so I want to keep this value. This is the estimation of f of 1.5. Okay, I want to keep that in my calculator right now. Okay, and then I want to go. I want to calculate this. It'd be alpha window, and then the absolute value of 3 is 3 over 4 factorial. So 4 alpha window 9, and then times, and then absolute value number 1, and it was 1.5 minus 2, and then come out of the absolute value and raise that to the fourth power. Okay, and that's what our error is going to be. Okay, for f of 1.5, that's how much we're off by, okay? All right, so let me go back to the our handout, our lesson, our notes, and we'll record this value. So from our calculator, we know that this number is 0.00 and then 78125. Okay, so that means our error has to be between negative 0.0078125 and positive 0.0078125. Okay, so what this means is this is our error. Okay, we're in between f of 1.5 plus this and f of 1.5 minus this. So we're going to show that. Okay, so we know that f of 1.5 has to be less than or equal to, okay, f of 1.5 plus this error. So plus 0.0078125, okay? But f of 1.5 has to be greater than or equal to f of 1.5 minus our error. So f of 1.5 minus 0.0078125. Okay, now what was f of 1.5? Okay, so that was that negative 4.958 that you're seeing right here at the top of your screen right here. Okay, and that's still on our calculator. So we're going to go back to our calculator and we're going to put the values in here. Okay, and f of 1.5 will be somewhere in between these two numbers that we get. Okay, so this number right here, negative 4.95833, and so on, okay, that's our estimation, and this is our error, okay? So what we can do is we can go on top and press enter to kind of copy and paste that, and then we're going to do minus, and then our error, that, and press enter. And then we're going to do the same thing, but we're going to add the error. So this is our estimation. And then this is our, and then we need to add to that. So plus. And then we need to go up to our error and enter on that. Okay. And press enter, and we get this value, right? All right. So I'm going to go back and record these values back on the notes page. All right, so back on our notes page, okay, what we have is this calculation came out to be negative 4.966 is less than or equal to f of 1.5, which is less than or equal to, and these two added together is negative 4.951. Okay, so what this is telling us is that f of 1.5 has to be in between this and this. Well, negative 5, okay, where's negative 5 in this? Well, negative 5 is even smaller than this, right? So there's no way it could ever be f of 1.5, okay, can ever be equal to negative 5, okay? All right, so that explains why right here, okay, that explains why f of 1.5 cannot be equal to negative 5. So we could say something like this. Therefore, f of 1.5 cannot equal negative 5. Okay, and that's how you answer part B. All right, for part C, okay, we want to write a fourth degree Taylor polynomial p of x for g of x is equal to f of x squared plus 2 about x equals 0, okay? Use p to explain why g must have a relative minimum at x equals 0. All right, so we know that g of x, okay, is just putting x squared plus 2 into the f function, okay? So from part A, we found that the Taylor polynomial for f, okay, and we could write this, f of x can be approximated with the third degree Taylor polynomial, right? Which is equivalent to, now f of x is an approximation for the third degree Taylor polynomial, okay? And then the Taylor polynomial is equivalent to this. So it was -3 plus 5 times, and then it was x minus 2, and then plus 3 halves times x minus 2 squared, and then minus 4 thirds times x minus 2 cubed, okay? So g of x, all right, okay, could be found by putting x squared plus 2 in for f. So if we put x squared plus 2 here, right, okay, so g of x is equal to f of x squared plus 2, right? Okay, so then all we have to do is, where we see x everywhere in this third one, is replace it with the x squared plus 2, because that's all it is a substitution, right? It's a composition of functions, okay? So g of x can be approximated with this Taylor polynomial p of, we're calling it capital P of x. Okay, now we only need to go up to the fourth power, okay? So it's going to be -3. There's no place to put this x squared plus 2 in that part of it. So -3 plus 5 times, and this x becomes x squared plus 2 minus 2. All right, so right now, okay, we have a second degree because we have an x squared. If we multiply this out, it'd still be x squared, okay? And then right here in this next one, we'd have plus 3 halves times x squared plus 2 minus 2, and we would be squaring that, right? Okay, so when we square this, look what happens, okay? When we square this inside here becomes x squared, but when we square it, this would become x to the fourth. All right, so that's it. That's our fourth degree Taylor polynomial. We just need to clean it up a little bit, okay? All right, so p of x is equivalent to -3 plus 5 and x squared plus 2 minus 2. These are going to cancel each other out, so 5x squared. And then this would be plus 3 halves, and then x squared, so that'd be x to the fourth. Okay, so when we say fourth degree Taylor polynomial or fourth order, that's this one, okay? So fourth order, fourth degree, same meaning, okay? All right, so now what we want to take a look at is, what's the fourth degree Taylor polynomial for g of x, okay? So let's take a look at this, okay? So this would be g of 0 plus g prime, because we're doing this at centered at x equals 0, g prime of 0 times x to the first over 1 factorial, which we wouldn't need to write, okay? And then plus g double prime of x over 2 factorial. You know what? I said g prime of x. It's g prime of 0. Let me fix that. Okay, so g prime of 0. Okay, times x squared. Okay, now this is the same as these up here. So we know g of 0 would have to be equal to -3, and g prime of 0, okay, well, there's no x term up here, right? Because this is where we get the x term, okay? So we know from this, g of 0 is the constant, so g of 0 would equal -3. From this, there's no x term up here, right? There's no coefficient of x, because that would mean that this g prime of 0 would have to be equal to 0. Okay, and here's my x squared term, right? Well, this means right here that this is the same as 5. So g double prime of 0 over 2 factorial has to be equivalent to 5. All right. So now, why is this one important right here? This is a giveaway of like how we're going to do this. Okay. So g prime of 0, how are we going to show that there's a relative minimum? All right. So g prime of 0 is equal to 0. That's a horizontal tangent. Okay. So we could have either relative min or relative max at x equals 0 right now, possibly, if it changes. Okay. Or if we look at the concavity. Okay. So we can't tell if g prime is changing from positive, negative, or negative to positive. But we can look at G double prime, and G double prime tells us about concavity, and we know G double prime of 0 over 2 factorial is equivalent to 5, which would mean G double prime of 0 is equal to 5 times 2 factorial. So that would mean G double prime of 0 is equal to 5 times 2, which is 10. Okay, so that's telling us that the second, let me slide this up a little bit. That's telling us the second derivative at 0 is 10. Okay, so that's telling us that G is concave up, right? So if G is concave up and you also have a horizontal tangent at x equals 0, then that must mean that there's a relative minimum at x equals 0. Okay, so we would say G must have a relative minimum at x equals 0 because we have G prime of 0 equal to 0 and G double prime at 0 is greater than 0. Okay, so that means there's a horizontal tangent at 0, and at 0 it's concave up. That would mean there's a relative minimum. That comes from the second derivative test. Okay, so let me slide that up a little bit. G must have a relative minimum at x equals 0. Okay, all right, so that's part C. That's from the 1999 exam.